This is the video lecture for Part 2 of Section 1.2, Divisibility. In this video, we're going to examine the Euclidean algorithm. The Euclidean algorithm is an efficient procedure for computing the greatest common divisor of two integers. It involves applying the division algorithm repeatedly until we obtain a remainder of 0. Now first note that for any integer a and minus a have the same divisors. Therefore, the common divisors of two integers a and b will be the same as the common divisors of a and minus b. And this implies that the GCD of a and b will be the same or equal to the GCD of a and minus b. And similarly, it follows that the GCD of a and b will be equal to the GCD of minus a and b, which will equal the GCD of minus a and minus b. This implies that we only need to consider positive integers when computing the GCD. We're now ready to state the Euclidean algorithm, so let a and b be positive integers with a greater than or equal to b. If b divides a, then the GCD of a and b is just equal to b. If b does not divide a, then we apply the division algorithm repeatedly as follows. So we start by dividing b into a to obtain a quotient q0 and a remainder r0. Then we divide the remainder r0 into b, and we obtain a quotient q1 and a remainder r1. Then we divide the new remainder r1 into the previous remainder r0, and we obtain a quotient q2 and a remainder r2. We divide r2 into r1, obtain a quotient q3 and a remainder r3, and we continue this procedure until a remainder of 0 is obtained. Now the remainders are getting smaller at each step, so eventually, and the remainders are always non-negative, so eventually we have to obtain a remainder of 0. And so this must occur after a finite number of steps, that is, for some integer t, we'll obtain r sub t minus 2 is equal to r sub t minus 1 q sub t plus r sub t, and then finally r sub t minus 1 will be equal to r sub t q sub t plus 1 plus a 0 remainder. So at this step we obtain a 0 remainder. And then the conclusion of the theorem is that r sub t, the last non-zero remainder, is the greatest common divisor of a and b. Now when applying the Euclidean algorithm, we start by dividing b into a, then the divisor in each line becomes the dividend in the next line, and the remainder in each line becomes the divisor in the next line. So we're starting by dividing b into a, and in the next step, the divisor b becomes the dividend, and the remainder r sub naught becomes the divisor. And then the next step, the divisor in the second step, r naught, becomes the dividend in the third step. The remainder r1 in the second step becomes the divisor in the third step. And we continue this. Now before proving the theorem, let's illustrate the procedure with an example. So we want to compute the GCD of 803 and 154. So we'll start by dividing 154 into 803, the smaller number into the larger. And we obtain 154 goes into 803 5 times with a remainder of 33. So we obtain a quotient of 5 and a remainder of 33. In the next step, we're going to divide the remainder 33 into the divisor 154. And 33 goes into 154 4 times with a remainder of 22. Next, we divide the remainder 22 into the divisor 33. 22 goes into 33 1 time with a remainder of 11. And then we divide the remainder 11 into the divisor 22. And we obtain 22 is equal to 11 times 2 plus 0, so we obtain a 0 remainder. And the last non-zero remainder is 11, and this is the GCD. Now, according to Theorem 1.2, the GCD of 11 can be written as a linear combination of the two integers 803 and 154. We can use the calculations in the Euclidean algorithm to obtain this linear combination. So we'll start by solving the next to the last equation for the remainder, which is the GCD. Then we use the preceding equations to substitute for each remainder. So our next to the last equation tells us that 11 is equal to 33 minus 22 times 1. We're going to substitute for the remainder, 22, and that was 154 minus 33 times 4 from the previous equation. And then we want to simplify this before we go to the next step. So you can see that this is 33 minus 154 times 1 plus 33 times 4. And so now we've got two terms with a factor of 33, and we can group those together. This is 33 times 5 minus 154 times 1. Now we're going to substitute for the remainder 33. And this is 803 minus 154 times 5. And so this is times 5 minus 154 times 1. And now we want to simplify this. So this is 803 times 5 minus 154 times 5 is 25 minus 154 times 1. And now we've got two terms that involve 154, and we can group those together and obtain 803 times 5 minus 154 times 26. And so now this gives us 11 written as a linear combination of 803 times and 154. So 11 is 803 times 5 plus 154 times minus 26. Now, in order to prove the theorem, we need the following lemma. And this says for all A, B, Q, and R in Z, if A is equal to BQ plus R, then the GCD of A and B is the same as the GCD of B and R. So this is saying if these four integers A, B, Q, and R are related according to the division algorithm, then the GCD of the dividend A and the divisor B will be equal to the GCD of the divisor B and the remainder R. So to prove this, we'll suppose A, B, Q, and R are arbitrary integers. We'll suppose our hypothesis that A is equal to BQ plus R, and we need to show that the GCD of A and B is equal to the GCD of B and R. Now to show this, we want to show that A and B have the same common divisors as B and R do. So let's suppose that C is an arbitrary non-zero integer, and let's first suppose that C is a common divisor of A and B. We then need to show that C is a common divisor of B and R. Now since C is a common divisor of A and B, then C divides A and C divides B, which implies that A is equal to CS and B is equal to CT for some integers S and T. Then R is equal to A minus BQ will be equal to CS minus CT quantity times Q. And we can factor a C out of this, and this will be C times S minus TQ quantity. And this implies that C divides R, since we have R is equal to C times an integer. So it follows that C will be a common divisor of B and R. Now suppose C is a common divisor of B and R, and we want to show that C is a common divisor of A and B. So since C divides B and C divides R, then B equals CX and R equals CY for some integers x and y. Then A is equal to BQ plus R will be equal to CX times Q plus CY, and we can factor a C out of that and obtain C times XQ plus Y. And this implies that C divides A, since A is equal to C times an integer. And therefore C is a common divisor of A and B. Since the common divisors of A and B are the same as the common divisors of B and R, then the greatest common divisor of A and B must be the same as the greatest common divisor of B and R. Thus, the GCD of A and B is equal to the GCD of B and R. And this proves the lemma. So we're now ready to prove the theorem. So let's just restate the theorem one more time. So we've got A and B are positive integers with A greater than or equal to B. If B divides A, then the GCD of A and B is B. If B does not divide A, then we apply the division algorithm repeatedly. And after a finite number of steps, we obtain a remainder of 0. Then R sub t, the last non-zero remainder, is the greatest common divisor of A and B. So we have two cases to consider. So B divides A and B does not divide A. So first suppose that B divides A. Then there exists an integer q such that A is equal to BQ, which is equal to BQ plus 0. And the lemma then implies that the GCD of A and B, the dividend and divisor, is equal to the GCD of the divisor and remainder, which will be the GCD of B and 0. And the GCD of B and 0 is just going to be B. So the greatest common divisor of B and 0 is equal to B, since B divides B and B divides 0. And B is a positive integer, so it's going to be greater than anything else that divides B. So this is the first case. Now let's suppose for the second case that B does not divide A. Then we'll apply the lemma repeatedly to each division in the theorem. So our first division is A is equal to BQ0 plus R0, and so the lemma tells us that the GCD of A and B will be equal to the GCD of B and R0. At the second step, we obtain B is equal to R0 times Q1 plus R1, and the lemma implies that the GCD of B and R0 is equal to the GCD of R0 and R1. At the third step, we have R0 is equal to R1Q2 plus R2. By the lemma, the GCD of R0, R1 is equal to the GCD of R1, R2. And the fourth step, we have R1 is equal to R2, Q3 plus R3. So the GCD of R1 and R2 is equal to the GCD of R2 and R3. And we continue this until we obtain R sub t minus 2 is equal to R sub t minus 1 Q sub t plus RT. And the lemma tells us that the GCD of RT minus 2 and RT minus 1 will be equal to the GCD of RT minus 1 and RT. And finally, at the last step, we obtain R sub t minus 1 equals R sub t times Q sub t plus 1 plus 0. That's when we obtain a 0 remainder. So by the lemma, the GCD of R sub t minus 1 and R sub t will be equal to the GCD of R sub t and 0. It then follows that the GCD of A and B is equal to the GCD of B and R0 by the first line, and the GCD of B and R0 is equal to the GCD of R0 and R1 by the second line. And continuing, this is the GCD of R1 and R2 equals all the way down to the GCD of R sub t minus 1 and R sub t, which equals the GCD of R sub t and 0, which is going to be equal to just R sub t. And again, since 0 is divisible by any integer, the GCD of R sub t and 0 will be equal to R sub t. And that's what we needed to show, that the GCD of A and B was the last non-zero remainder, which was R sub t. And so this completes the proof.